student, we will start the next chapter of organic chemistry, that is the hydrocarbon. In that, first topic is alkanes. Alkanes, this is your aliphatic hydrocarbon and saturated. This is aliphatic and saturated hydrocarbon. So you have to do is nomenclature and isomerism, which I have already taken earlier, and so you can revise from there isomerism and its nomenclature. So straight away we come to the preparation of alkane. The first method is given, that is from sodium salt of carboxylic acid. In this you have to do two methods. One method is a decarboxylation of sodium salt and here you will be using the carboxylic acid. This is your carboxylic acid. You have to use sodium salt, so this H will be replaced by sodium. This is sodium carboxylate, and this is treated with soda lime. Soda lime is a mixture of these two, and this quick lime is in traces. So this is soda lime and heating is done, and this is around 360 degrees Celsius. If you take 2 Kelvin, so it is 630 Kelvin. Different values are there, so heating is important. And so here sodium carbonate is decarboxylation. Carboxylic group is decomposed. So Ne2CO3 is out and RH is formed, and Ne2CO3 byproduct. This is alkane. So if you start with R as CH3 and rest as it is, so you will have on heating, same this temperature soda lime, and this is your Ne2CO3 will be out, and you will have methane. If you take in place of this C2H5, so here it will be C2H6 ethane. This is sodium. This when it was CH3 CONA, this was methane. This is sodium acetate. Okay, and IUPAC name 2 carbon, so ethanoate, sodium ethanoate, that is the name, so common name this is. And if you take C2H5, here it will be C2H6 ethane, then 3 carbon, so it will be sodium propanoate, and so on. So this way you can prepare alkane from decarboxylation. The second method is Alkanes synthesis. The second method from sodium salt of carboxylic acid, but by coal base synthesis. This is an electrolytic process. Electrolytic process. So wherever coal-based synthesis you see, it is always electrolysis taking place. So carboxylic acid salt, sodium carboxylate, solution is taken and this will decompose into its sign carboxylate ion and sodium ion. This is carboxylate ion. This will be attracted at anode and this will be attracted at cathode. Our aim is to get organic part, so we will be aiming at anode, reaction at anode. So at anode, this carboxylate ion will be attracted, will lose one electron and will turn into neutral carboxylate molecule, and this electron which is formed here will be passing and reaction will be carried on. This neutral carboxylate molecule which has carbon with two free oxygen, I have taught to you earlier, will release automatically carbon dioxide and R will be free. So if we take two molecules of this, then 2R, R will be bonded with R and this is your alkane. Here then also you will have to take 2, this is 2, this is 2, this 2, this 2 and this 2. So here in the previous case where you decarboxylated sodium salt, you got alkane, even methane you could obtain. But by this process you can't obtain methane, at least 2 carbons should be there. So we can obtain alkane from sodium salt of carboxylic acid by these 2 methods. Now next method of preparation is from alcohol. From alcohol. Alcohol combines with hydroiodic acid in the presence of red phosphorus at 423 K. Temperature is important to remember. Without red phosphorus, this reaction will not take place. So we will have RH form, water will be out. If I take this 2, RH will be there, water will be formed and iodine will be liberated. So this RH is your alkane and this is your alcohol. If this R happens to be CH3, then this R will be CH3, it will be methane. If this R happens to be C2H5, ethyl alcohol, then we will have here C2H5 and H, so that will be ethane, and so on you will be obtaining. Now third method is from aldehyde. The third method is from aldehyde. Aldehyde is R C double bond OH HI, that same, and temperature is 473. Your temperature is little higher, remember that. And we will have, I'll show you how the reaction will be there. Water will be there, I2 will be formed, no doubt. This oxygen is gone out with the water H2O, and here in place of this your we will have to balance it further. So this is here, oxygen is gone with water, so here 2 hydrogens will be attached. So we will have RCH3 form Okay, this is all satisfied there. One hydrogen here, one hydrogen here, two hydrogens and two hydrogens for water. So 4 hydrogens, so we will take it 4Hi. 4Hi, and so it will be 2I2 and reaction is balanced. So this is alkane. So we do not get from aldehyde methane, but from alcohol we could get methane. Okay. Next method is from Grignard's reagent. Fourth method is from Grignard's reagent. Grignard's reagent, I mentioned you while I was teaching you mechanism. Carbanion, then I had mentioned this is RMGX. This is Grignard's reagent, organometallic compound. And when this is treated with any compound which has active hydrogen, so with alcohol or with water. So with water, when it reacts, we get, if I differentiate this R with this R, so that you can know which R of which group is going where. So what we will have, the bond will be splitting from here, you know, this is minus, this is plus, and here this will be there, we will have, this is a splitting, here minus and this will be plus. So plus minus we will have R dash and we'll have MgOHX. And here if I write reaction same way, breaking, plus and minus, so we'll have RH plus MgXOH. This is alkene and this is also alkene. So from this you can prepare higher alkane but not methane from alcohol. This is alcohol. And when it reacts with water, we can get any alkane, even methane can also be obtained. Now next reaction is Wood's reaction, fifth method, that is Wood's reaction. Fifth method, from alkyl halide, that is Wood's reaction. Name reactions are very important, student. This reaction is very important because of its name reaction. Name reactions are asked directly as short notes or direct conversion or your different reaction to identify multiple choice. Different way this is asked. Even fill up the blank, correct the statement. Different ways this is asked. Wood's reaction, in that alkyl halide, two molecules, both are alkyl halide, they combine with sodium metal in the presence of dry ether. If no dry ether, it is no reaction and it is not Wood's reaction. So NaX will be formed. 2NaX will be the byproduct and we will have R bond R, that is alkene. So you cannot obtain by this method your methane. Higher alkanes can be obtained by Wood's reactions. Today's method, that is removed from the syllabus for this year. So you have not to do Corey's method. Now we come to the physical properties. Physical properties. First is physical state. I have written down to save time so that you will have all points before you. So physical state, from carbon 1 to carbon 4, they are in the gaseous state, and C5 to C17 in the liquid state, and C18 onward solid, waxy solid at ordinary temperature and pressure. Room temperature and pressure. Now, boiling point, these are the important points. 1, 2, 3 and 4. They have lower boiling point than other classes. Other classes means alkyl halide or alcohol, that's it, with same molecular weight. If an alkane and an alcohol they have same molecular weight, then the alkanes will have lower boiling point, and that is due to low polarity or no polarity. So remember that point. Second is, in a straight chain isomer, when alkanes are having a straight chain, not branching, in a straight chain isomers, that a boiling point regularly increases, regular increase in boiling point. But carbon 1 to 4 are exception. There is no increase in their boiling point, although they may have the straight chain. Third point, boiling point increases by 20 degrees Celsius to 30 degrees Celsius for each CH2 unit. If you have a methane, or take carbon 4 above, that is C5H12. Carbon 5, this is above, and you take C6H14. 1 CH2 unit is more. So the difference in the boiling point will be of 20 degrees Celsius to 30. This will be having 20 degrees Celsius temperature, boiling point less than this. So that is what it means. Branch chain have lower boiling point than their straight chain. So if this I explain to you here, suppose you have this compound 1, 2, 3, 4, 5. This is your straight chain pentane, normal pentane. And if you make this isomer CH3H, H2H3, this is having one branch, and here you take another, that is 1, 2, 3, CH3, CH3 and CH3 and CH3, all are having 5 carbons and 12 hydrogen, all of them are having. So this is the straight chain, branch, more branch. So what have you written? Branch chain have lower boiling point than their straight chain. So this is if A, this is B and C. So the boiling point of C will be less than the boiling point of B, and the boiling point of B will be less than the boiling point of A. That is what it means. Then melting point increases with molecular weight for straight chain. So that is number of carbon will increase in the straight chain, then melting point will increase, but the strength will not be regular, not with a fixed intervals, it will not be changing. Increase in more, melting point increases more for odd to even. If you go from odd to even, then melting point increases more. But when you come from odd to odd, one odd to another odd, like propane and then pentane. So one odd to another odd, when you go odd to odd, the increase in melting point is less. But when you come from propane to butane, that is from odd to even, then this increases more. So this is density. Density increases with increase of molecular weight. More will be the number of carbon atom. In alkane, more will be density, but they are lighter than water. Alkanes are lighter than water. Okay, now chemical properties. First is combustibility, burning in the air, alkane, any alkane, lower or higher, in air will form carbon dioxide and water along with the heat, exothermic reaction. Then controlled oxidation, that is when you pass air or directly oxygen but in the presence of catalyst, different condition, then products are different. So that you have to remember. Here lower alkane, copper, when copper is the catalyst, temperature is so much, pressure is so much, we get methanol. When methane is the alkane, oxygen is passed but molybdenum oxide is taken as catalyst. We do not get alcohol, we get formaldehyde. We take any higher alkane and pass excess of oxygen, then we get in the presence of manganese acetate, which is a catalyst, we obtain carboxylic acid. So different products are obtained under different condition. Here ratio is 1:9:1. Okay. Then chlorination reaction with chlorine. First reaction you have done, that is methane combining with chlorine in the presence of sunlight, and you obtain CS3Cl plus HCl. This reaction you have studied in class 10. Once more it will react and all the hydrogens will be removed, and excess of chlorine when we take, we will get CCl4 and HCl. This is your free radical. This we have done in mechanism part. So that portion you will revise from the mechanism. Free radical substitution reaction we have done in mechanism portion. Second kind of reaction is when methane is taken with chlorine in direct sunlight, then carbon is formed, black color. This is a gas, this is gas, colorless gas, colored gas, and here we get black residue. And this reaction is explosive. And the same reaction when it takes place at 20 degrees Celsius, these two combine at 20 and darkness is there, then no reaction takes place between these two, and in dark no reaction takes place at 20 degree. These two you take and temperature you keep 250 degrees Celsius and darkness is there but temperature you have increased to so much, or if you keep so same temperature this but you take sunlight, then reaction will continue. This reaction continues. Here in this case no reaction, and here reaction will be going on till the end. Then aromatization, that is this is alkane, is 6 carbon long chain, is converted to benzene. Benzene is your having this structure 6 carbon with a double. So this is at these conditions, this was temperature, pressure, and these are your catalyst oxides of chromium, vanadium and molybdenum in the presence of alumina over alumina. Then we obtain benzene this and hydrogen. So this is cyclic compound is formed. So this is your cyclization also called reforming. Next property is isomerization. A straight chain has formed, that is branch chain compound under this condition. 4 carbon, here also 4 but the branch. This is butane, this is 2-methyl propane. And the last is pyrolysis, and that I will explain you over here. Pyrolysis, that is also called fragmentation or cracking. So in this case pyrolysis, if I take example of propane, and if this is heated to 600 degree, pyrolysis means heat breaking by means of fire. Fire is fire. So breaking by means of heating. So there will be 2 reactions. One will be your when carbon-carbon bond will break, and the other will be when carbon-hydrogen bond will break. So when carbon-carbon bond breaks, then this is always followed by carbon-hydrogen bond breaking. Or it may be simply carbon-hydrogen bond will break, not carbon-carbon. Then so we will get different compounds. So if carbon-carbon bond will break, so we will have CH3 one piece and CH2 and CH3 another piece. These two pieces, okay? So as I told, when carbon-carbon bond will break, then carbon-hydrogen bond will also break. So from here, one carbon-hydrogen bond will break. So one hydrogen which will be free from here will be taken up by this. So this will be, and here double bond. So we will get lower alkane and we will get an unsaturated hydrocarbon alkene. And when only this is taking place, so we will have an alkene form with the same number of carbon atom. So this can take place in long chain compound also. So we get mixture of lower alkane and alkene. So that's all about your pyrolysis and uses you will read from the book. And next chapter I will be teaching alkenes. So till then, bye.